Thank you for your introduction. Can you see my screen?
Yeah, it's great.
Okay. So today I would like to talk about gauge theory on form manifold with periodic ends. And I'm Masaki Taniguchi, working at Riken in Japan. And there are three contents in this talk. In the first part, I will talk about historical backgrounds of form manifold, gauge theory on non-compact form manifolds. In the second part, I will focus on the Yang-Mills gauge theory on form manifold with periodic ends. And I also would like to talk about application of such a gauge theory. As an application, we would like to construct obstruction to codimension 1 embedding of a certain class of homology spheres. In the third part, if I have time, I would like to talk about alternative proof of the second main result without using gauge theory on form manifold with periodic ends. And this slide is available from my website. And my website can be found by Googling my name. So if you're interested in my talk, you can download it. Okay, so let's start the talk. So let's go to the first part, the background of gauge theory on non-compact form manifolds. Before going to that, we first review the gauge theory on closed form manifold. So let X be oriented closed smooth Riemann form manifold. And there are two theories which are mainly considered. So in the Yang-Mills gauge theory, we fix a SU2 bundle over X. And for any connection on P, we can consider the ASD equation given by this. And this FA is a curvature of A, and star is a Hodge-Stack operator of X. Okay? And this is called ASD equation. In Seiberg-Witten side, we fix a spin-sheet structure over X. Then, for a pair of spin-sheet connection and positive spinor, we can define the Seiberg-Witten equation given by this. So this dA phi is equal to 0, where dA is a Dirac operator with respect to the spin-sheet connection A, and we also consider this equation. So this is the same as this one. And we consider the phi phi star 0, and 0 is the traceless part of phi phi star, and the rho is coming from the Clifford multiplication. So this is called the Seiberg-Witten equation. And in both sides, we can define the moduli space of solutions. In Yang-Mills gauge theory, we consider all the solutions divided by automorphism. And also in the Seiberg-Witten side, we also consider all solutions divided by automorphism. And note that the Seiberg-Witten moduli space is compact. So this is special situation in Seiberg-Witten theory. Okay. And by analyzing these moduli spaces, we obtain information of original manifold X. And I also want to fix the notations of basic quantities of form manifolds. So fixed orientation of X, we can define the intersection form by using a cup product. Then we denote by B plus X the dimension of positive island spaces of the intersection form, and B minus is a negative one. And signature is defined as a difference between them. Okay. And now we review the two theories in the viewpoints of constraints. So this is some restriction and invariance of smooth form manifolds. Okay. So in Yamini's gauge theory in 1982, Johnson proved a significant result of smooth form manifolds, which is called Theorem A. And this is a theorem for manifolds whose B plus is equal to 0. This theorem implies any closed definite form manifolds have standard intersection form. And there is an alternative proof of Theorem A in the Seiberg-Witten side. And there is also constraints of spin form manifolds by using Yamini's gauge theory, which are called Theorem B and Theorem C. And these theorems work for spin form manifolds whose B plus is equal to 1 and 2. And for such a simply connected spin form manifolds, the intersection forms are restricted as 0110 and 2 times 0110. And this is called theorem B and C. And there is some alternative proof in the Seiberg-Witten theory. This is due to Bronheimer. And in the Seiberg-Witten side, we have more stronger constraints on the intersection form, which is called 10 over S inequality. So for spin form manifold whose B plus is equal to greater than 0, we have this inequality. And this is due to filter. And these are constraints coming from Yamini's and Seiberg-Witten gauge theory. On the other hand, for form manifolds whose B plus is greater than or equal to 2, we have two invariants, so Donaldson invariants and Seiberg-Witten invariants. Okay. And these invariants are related to each other by Witten conjecture. Okay. And moreover, in the Seiberg-Witten side, there is some homotopy theoretic refinement of Seiberg-Witten invariants, which is called the Bauer filter invariance. So when we define such an invariant, we regard the Seiberg-Witten map as a map from some infinite dimensional space to some infinite dimensional space. And we approximate this map by these finite dimensional subspaces. And we obtain a continuous map from finite dimensional sphere to some finite dimensional sphere. And then the stable homotopy class of this map is called the Bauer filter map, invariant. Sorry. And the relation between Seiberg-Witten invariants and Bauer filter invariant is as follows. So mapping degree, a relation between mapping degree and homotopy class of map. So this is a relation. And when we define such an invariance, we use the boundedness of Seiberg-Witten modular space. So that's the reason why we cannot define the Bauer filter type invariants in Yamini's gauge theory side. And this is a review of Yamini's gauge theory or Seiberg-Witten gauge theory for closed form manifolds. So do you have any question? Okay, so let's go to the second part. So today I would like to consider the following question. So how can we develop gauge theory on non-compact form manifolds? And today we focus on the following three types of non-compact form manifolds. The first one is form manifold with cylindrical ends. So this is like this. So we have non-compact manifold which have this product end. So Y is a 3 manifold. And when we consider the gauge theory, we need to consider the Riemann metric, and we fix the Riemann metric, which is product on this part. Okay. So this is the first class. The second class is form manifold with periodic ends. So this is the main topic in this talk. So on this non-compact form manifold, we have the end corresponding to a Z cover of closed form manifold. And when you take x is equal to y times s1, then we can recover y times r. So yeah, the first class is a special case of second class. And when we consider the periodic and for manifolds, we use a Riemann metric, which is periodic on this part. Okay. And moreover, I also want to mention about the gauge theory on the form manifold with conical ends. So like this. As a manifold, this is diffeomorphic to the first one, but we use a different metric. So ds squared plus s squared zy. Okay. So today I would like to focus on these three non-compact manifolds. So first, I would like to talk about the form manifold with cylindrical ends. Actually, Fourier theory gives a general way to treat the modular spaces, Yang-Mills and Seiberg-Witten modular spaces for this X. Yeah, in 1988, Fourier defined the instant of Fourier's homology as a infinite dimensional version of Morse homology with respect to the Chern-Simons functional. And when we define this homology group, we analyze the moduli space, Yang-Mills moduli space for this manifold y times r. And there is some counterpart in the Seiberg-Witten side, which are called monopole Fourier homology. So this is induced by Kronheim-Moog and Markov-Bank. Okay. Sorry, I should say, so this is the invariant of the homology 3 sphere, and this is the invariant of the spin-sheet 3 manifold. And moreover, we can also define the relative Donaldson invariants by counting the moduli space on this. So for given for manifold with boundary, we can have associated cylindrical end for manifolds, and counting the moduli space on this, we can define the relative Donaldson invariant. And in the Seiberg-Witten side, we can also have such kind of thing. On the other hand, we can also prove Donaldson theorem A for manifold with boundary. So we need to assume that B plus of this part is equal to 0. Then, yeah, Freud proves some inequality. So this is some invariant of the intersection form, and this is called Freud invariant. And when the boundary is equal to S3, we can this inequality recovers the original Donaldson's theorem A. And there's some counterpart in the Seiberg-Witten side. Okay. And yeah, there is some manifold with boundary version of theorem B and C for manifold with boundary. Yeah, this is due to Fukaya Furuta. And also in Seiberg-Witten side, there are theorem BC for manifold with boundary. This is due to Branches Green. And on the other hand, 10/8 inequality also proved for manifold with boundary. This is due to Manorescu. And in the proof, instead of Fourier homology, Manorescu used the Fourier homotopy type. And this is some homotopy theoretic refinement of the monopole Fourier homology. So this is a review of Yang-Mills or Seiberg-Witten gauge theory for the form manifold with cylindrical ends. So do you have any question? Okay, so
what I'm sorry, I will ask a question. What conditions do you have on the boundaries in order to get these inequalities?
Sorry, I couldn't hear the.
What conditions do you put on the boundaries to have these inequalities?
I see. Okay. So in the case of Monolesque, we need to consider that where is rational homogeneous sphere, and also also I think here we also need why is rational homogeneous sphere. And in the case of Yam's gauge theory, we need to impose a condition why is homologous sphere. That's a condition. Yeah. So okay. Okay. So yeah. Okay. So let's go to the second part. In this part, we focus on the form manifold with periodic ends. So let me denote the fundamental segment of the end by W0. So W1 and W2 are copies of W0. And we consider the periodic metric. And then in 1987, Taubes proved Donaldson theorem A for form manifold with periodic ends under the assumption that Y is a rational homology coefficient from Y to itself. And also we impose there's no non-trivial representation, SU2 representation on the fundamental group of Wi. So this is essential condition. And under this assumption, Taubes proved the intersection of form of this part is standard if intersection form of this part is negative definite. And as an application, Taubes proved existence of uncountable family of exotic form. And in the Seiberg-Witten side, when you define the molecular Ruberman stability invariant for spin rational homology S1 times S3, so this is some kind of Seiberg-Witten invariant for homology S1 times S3. But when you define such kind of invariant, the index of Dirac operator on this form manifold with periodic ends is used to define the invariant in order to prove independence on the perturbations or metric. So this is due to molecular Ruberman stability. Okay. And there is some Donaldson theorem B and C for form manifold with periodic ends under the same assumption of Taubes. This is due to Ota. Okay. And moreover, recently, Jean-Philippe Lin used the modular space, Seiberg-Witten modular space on this form manifold. So this form manifold contains both cylindrical and periodic ends to obtain a new obstruction to be symmetric. And Lin assumed this part has a periodic PSU metric and some homological assumption. So Wi is homology coefficientism from Y to itself, and Y is rational homogeneous. And Lin's constraints is given by this. So for any homology S1 times S3, oriented spin S1 times S3, and suppose, there exists a rational homogeneous sphere in X as a submanifold, which generates the H3 of X. And moreover, we need to assume X has a PSU metric, then this equality holds. And this is called molecular Ruberman stability invariant. And this is a Flow-Shop invariant with respect to the restricted spin structure. And moreover, there is some Bauer-Fulton invariants for under the similar assumption of Jean-Philippe Ring, and this is due to Beloso. And today we focus on the following two results. So first one is the compactness. First, we show the compactness of modular space, Yamil's modular space for this whole manifold under some energy condition. Although Taubes imposes some topological condition, but in this result, we don't need impose any condition, but we consider some subspace of the modular space, which is coming from energy condition. As an application, we obtain some obstructions to embeddings of three manifolds, homology three spheres into homology S1 times S3. So today we focus on the proof of this result. This is today's topic. And in next time, we focus on this second result. And this result is joint work with Hokuto Konno. And we will prove 10 over 8 type inequality for this four manifold, a spin periodic and four manifolds. But we impose existence of periodic PHC metric on the end. And as an application, we construct new obstruction to PHC metric for spin rational homology S1 times S3. Okay. So this is a review of the gauge theory for manifold with periodic ends. Okay, so do you have any question? Okay, so and I also mentioned about the four manifold with conical ends. So in Cyberwitten side, this is only for Cyberwitten side. Kronheim-Roker defined some Cyberwitten type invariants for four manifold with contact boundary. And when you have contact structure on the boundary, we can construct almost a Taylor cone. And there is some canonical solution on the end. If you part out the Cyberwitten equation on the end, then by counting the Cyberwitten modular space, Kronheim and Morgan define some invariant for manifold with contact boundary. And there is some relative version of the Kronheim-Morgan's invariant, which is called the contact invariant. So for any contact three manifold, by considering the modular space for this four manifold, so this has cylindrical end and conical ends. So by counting the modular space on this space, Kronheim-Morgan's Bastavo defined some contact invariant, which lies in the HM check minus Y. And recently, Ida introduced powerful type refinement of Kronheim-Morgan's invariant, and this is powerful type invariant. So this invariant lies in the stable homotopy group in some degree, and this recovers the Kronheim-Morgan's original invariant. And recently, last year, I and Ida introduced some homotopy theoretic refinement of this invariant. So Kronheim-Morgan's invariant. So this is stable homotopy class of a map from S0 to some suspension of the Cyberwitten Fourier homotopy type. And because we can use the other generalized homology theory rather than singular homology theory, we can obtain a K-theoretic contact invariant using such kind of thing. And okay, so so this is the review of gauge theory on four manifold with conical ends. So do you have any question? Okay, so And I should mention about the related topics, which I cannot mention today. The first one is Fredholm theory or index theories for such a non-compact Hall manifold type 1 to 3. So yeah, there are many studies. Yeah, Lockhart, West, Atiapat, Singer, Moroka, Ruben, Sabriev, and Kronheimer, Moroka. And gauge theory is based on these theories. So these theories are very important in our study. And on the other hand, there are some kind of upward gauge theory or gauge theory for singular connections. So when the singularities are isolated, for example, Finkelstein developed Yamil's gauge theory for such kind of thing. And when the codimension of the singularity is equal to 2, Kronheimer Moroka developed the theory for Yamil's gauge theory for such kind of orbifolds. So these are related topics, but I can't say anything. Okay. So yeah, this is the first part of my talk. So do you have any question? Okay, so let's go to the second part, main result. So in this part, we focus on the Yamil's gauge theory for manifold with periodic ends. So let Y be oriented homology S3 sphere and X be oriented homology S1 times S3, and fix generator of H3 of X. And in order to describe our main theorem, we will introduce the following two invariants. So one is invariant for this tuple, so XCJ, so this is the generator of H3. And output is, J is a positive integer. Output is some real number, which is denoted by QXCJ. So this is some kind of minimal value of Chern-Simons functional. And when you consider that X is equal to Y times S1, then this invariant is equal to minimal non-trivial critical value of SU2 Chern-Simons functional of Y. Yeah, I will explain later the detail of this invariant. And second, I also need Fourier theoretic invariant. So for any regular value of critical value of Chern-Simons functional, we can define the filtered instanton Fourier homology and some cohomology class, filtered cohomology class. And these are invariants of Y. And this filtered instanton homology is introduced by Fincher and Stern in 1992. Okay. So we need three invariants, Q, and this cohomology class theta, and this filtered instanton Fourier homology. And by using these invariants, our main result can be written as follows. So suppose the first cohomology of any SU2 flat connection on Y is equal to 0. And suppose there is some embedding from Y to X, so homology 3 sphere to homology S1 times S3. So this is smooth embedding such that the fundamental cross of Y is equal to C for given generator. Then the following conclusion holds. So for any real number which is smaller than minimum of these numbers, and I will explain Ly later. Anyway, so for such a real number, we can confirm that the cohomology class vanishes for this R. Where Ly is the number of the conjugacy classes of SU2 representation of fundamental group of Y. Okay, and note that if you have this condition, we can easily check this is finite. This Ly is finite. And the examples of the homology three sphere as follows. So sigma PQR. So if you consider the homology three sphere of sigma PQR, then this condition, this star condition is satisfied. Okay. And as an example,
What
sorry?
was the star condition again? I missed.
Okay, so star condition is for any SU2 representation on X, on Y, the first cohomology of the
Got it.
okay.
Thanks.
Yeah. And set Y as minus sigma 236K minus 1 for positive K. Then, we can check that this cohomology class does not vanish for R is equal to 1 over 2 in this cohomology. And moreover, when X is equal to homotopy S1 times S3, then we can, later I will check, we can check that Q of this X is equal to 1 for any C and J. So, as a conclusion, we see this cohomology class vanishes, but this gives a contradiction. So we can say that there is no embedding from Y to X as a generator of H3. And on the other hand, there is a locally flat embedding from Y to X as a generator of H3 this is due to Friedman. So Friedman proved that any homology 3 sphere can be embedded in R4, locally flat embedding in R4. So this result cannot be proved in the topological category. Okay. So so let's go to the definitions of these invariants. So first, for fixed homology, third homology class of X, there is some corresponding Z cover over X. So we fix a Z cover, and this is classifying map, and we take a lift. And so now we consider the subgroup JZ in the group Z. We divide X tilde by this action. Then we have J over JZ covering of space of X. So this is denoted by JX. Okay. And again, we have Z cover from the quotient. And here we consider the SU2 representation space of JX. And this, by holonomic correspondence, we can denote this space by this one. So SU2 by the one form divided by gauge group. And we denote by theta the product connection. Okay, now I can define what is Q. And before that, I will introduce the Chern-Simons functional on this set. So this representation space. So for any representation on JX, we represent this representation by a SU2 valid one form on JX. Then we consider the following integration. So trace of FAA which FAA. So FAA is the SU2 connection on X tilde. So this is a picture of X tilde. And this is the lift of classifying map, which is denoted by F tilde C. And on the negative part, on this part, this connection AA coincides with the pullback of A on this part. And on right-hand side, so positive part, this connection is zero connection. Okay, so then this integral is well defined because on red and blue parts, this connection is flat. So this is well defined. So this is the definition of Chern-Simons value of A. Okay. And we can easily see that this functional descends to the following map. So map from the representation space of JX to 0, 1. And now I define for a given type of xcj, we define qxcj by the minimum value of the Chern-Simons value of A and 1. And over the following conditions. So A is irreducible aesthetic representation of Ix, and I is greater than or equal to 1 and smaller than or equal to J. So this is the definition of the Q, invariant Q. And this is some, I should say, so this is irreducible one. So stabilizer is plus minus 1 part. Okay, now I go to the calculation of example. Do you have any question on this invariant? Okay, so let's go to the calculation example. So when x is equal to s3 times s1, then jx is equal to s3 times s1 again. Then there is no irreducible representation because the fundamental group is isomorphic to Z. So our invariant is equal to 1 for any J. And when you consider the homotopy S1 S3 times S1, the same result holds. And when you consider the y times S1, then Jx is also y times S1. So in this case, the pullback of connection gives the 2-1 correspondence from here to here. And we can also define the Chern-Simons. So this is a usual Chern-Simons function for y. And by the definition, this is actually the corollary of Stokes' theorem. We can see that this diagram commutes. So by using this, our invariant is equal to minimum non-trivial value of Chern-Simons function for irreducible aesthetic connections on Y. Okay. So this is an example of calculation. So next, I would like to go to the definition of filtered instant Fourier homology and the filtered homology class. So first,
may I ask a question? The previous page.
Okay. Sorry.
You take minimum to define the invariant Q over R star. Is R star compact?
Sorry, R star compact?
Yes. R star of IX.
IX, RX,
Yeah.
R star, RX.
Yes, I'm looking at the formula with the irreducible part written in red.
I'm sorry. I couldn't understand your question. So, sorry.
So the formula in the middle of the page, which defines Q
This
of
one?
X, C, J. Yeah, this is the formula. Yes. You are taking the minimum, right?
Yeah.
Is that the minimum over a compact space, or?
Oh, that's. Sorry.
I mean, does it exist?
So maybe if you have this condition, sorry, the covering space has this condition. So
okay.
Then this is compact. But in general, I don't know.
Okay. Okay. Thank you.
Okay, so let's define the instant of homology. So instant of homology is infinite dimensional Morse homology with respect to this function. So this is a function from By to S1. So By is defined by the quotient set of SU divided 1 form divided by the gauge group. And here the Chern-Simons is defined by this way. So we have some infinite dimensional space and one valid function. And when you part of the Chern-Simons function, the critical points are finite set. So instant Fourier homology is generated by these finite points, and differential is defined by counting the trajectories. And you can also define the z-graded version of instant Fourier homology by taking a z-cover of this infinite dimensional space and S1. So now here we consider the mapping degree 0 gauge transformation instead of full gauge transformation. Then the chance amount is well defined map to R. So we have some Z action. So there are infinitely many critical points, but still we define the instant Fourier homology when you consider the perturbation. Now I would like to consider the filtered version. So what is a filtered version? So this is infinite dimensional relative most homology with respect to this functional. So relative means we consider the most chain complex for this part. So there are critical points, and we consider the chain complex generated by these critical points. So this is a rough idea. And today we ignore the problems related to the perturbations because of this is just a technical part. So let y be oriented homologously sphere and gy be a Riemann metric. And then the filtered instanton chain group is defined by the following way. So this is generated by critical points of Chern-Simons function, but we consider the irreducible part. So and this critical point can be written as this equation, so flat connection over y. And we impose a condition the Chern-Simons of A is smaller than R, and Fourier index of A is equal to given integer. So this is some generalization of Morse index in this situation. And we can also define the differential on this chain complex by counting the space of trajectories. So this is that's completely same as Morse homology in finite dimensional case.
Oh, so I have a question. So I have a question. So in your definition, is a chain complex infinitely generated? So there will be like infinitely many critical points because of your restricted gauge group.
Actually, the answer is no. So because of this condition, generated is finite.
Okay.
Yeah, because how to say? So
wait, but you can go to negative infinity, like the value of the Chern-Simons functional.
But the point is that the Fourier index is fixed.
Okay.
Okay. Yeah. So yeah. So that's a good question. Yeah, but yeah. So this is actually finite because of this condition.
Okay.
Yeah. So now I'll count the space of trajectories. And in order to count this space, we need to give the structure of manifold on these spaces. And when you do this, we give a identification from the trajectory space to modular space of AST equation on this for manifold y times R. And we consider some asymptotic condition coming from the A and B critical points. And then one can see that delta square is equal to 0. And Fincher-Stern proved the following result. For any regular value of Chern-Simons functional, the chain homotopy type of this guy does not depend on the choice of Riemann metric and perturbations. So the point is here we take R as regular value. Then if you consider very small perturbations, then the chain homotopy type is very defined. This is the key point. And now we have chain complex. So we take a homology. So this is called the filtered instant of homology. Sorry. Now we are now considering homology because we want to consider some cohomology class. So now, here we consider the irreducible part. But if you consider the all parts, so all connections divided by gauge group, there is some very bad quotient singularities, which is called product connections. So this point. And by counting the trajectories converging to this point, and Ronson or Froelich filter defining some first cohomology class. Yeah, in our setting, we can also count the modular space converging to the trivial fat connection. So this is just a restriction of usual usual filtered cochain. So this is just a restriction. And this defines, I checked, this defines as a cohomology class. And if you take R as the regular value, then this class does not depend on the choice of Riemann metric and perturbations. Okay, so now I complete the definition of Q and filtered instant Fourier homology and the cohomology class. So now again, I want to confirm what is our main theorem. So under some assumption, under some technical assumption, suppose there is some embedding from Y to X such that the fundamental group of class of Y is equal to C. Then for any number R, which is smaller than this number, this equality holds. And now sorry.
Excuse me, just on the previous slide, saying that your invariant theta R is independent of all possible choices.
Yeah.
So clear because when you change your perturbations, you also change your Chern-Simons function somehow, right? I mean everything will be perturbed, right? It will be the perturbed Chern-Simons function. You'll have
So if you perturb the Chern-Simons functional, the perturbation will change, but the filtration will change. So if you perturb the Chern-Simons functional, this filtration will change. But if you take this as sufficiently small.
Yes, okay, that I believe. Okay, yeah, okay, so that is the condition. For small enough h, then the
that's the important point. Yeah. Thank you. So I will give the sketch of proof. So if we have embedding from Y to X like this, then we can cut X open along Y. Then we have cobordism from Y to itself. And so this is denoted by W0. And we define W. Sorry, do you have any question? No. So Wn infinity is defined as a union of Wn and Wn plus 1 and so on. And we in order to consider the Sobolev norm, related to Sobolev norm, we need to fix some function on tau on this space, which satisfy these conditions, where T is a shift map like this. So if you shift this function, the difference is just plus 1. Sorry, I should. So this is sorry. This is T. Sorry, this is T. No. This is tau. Sorry. So we have some function tau like this. Okay. So now I would like to give the compactness theorem of the S3 modular space. So suppose k is greater than or equal to 3, so integer, and delta is sufficiently small positive number, then first we should say, yeah, L2K delta norm on this one, this manifold, W1 infinity, is defined by this way. So using this tau, we can define the weighted norm. Then the following, we can consider the following modular space. So modular space for this manifold is defined as, yeah, SU2 value 1 form, which lives in this weighted norm, weighted solver space. And suppose this AC equation is satisfied, and moreover, the following condition is essential. So yeah, 1 over 8 pi square times L2 norm of curvature of A is smaller than this number. Then we need to consider the, yeah, gauge group in this setting. So this is L2K plus 1 local gauge transformation preserving the configurations. So this is called the ASP modular space. But yeah, we consider this condition. So this condition is essential to prove this lemma. So for any sequence in this modular space, we can take a subsequence and gauge transformation such that the Gj star A and J converges on W to infinity. So this is yeah, very important to obtain our main theorem. Yeah, I will give the sketch of proof. So sorry, I don't have enough time. So yeah, so let AN be a sequence in the modular space satisfying this condition. Because by the definition of Q, the energy, so this is called the energy is smaller than 1, so there is no bubble. Bubble means this sequence, like this sequence. So let T be the following connection on the R4. So yeah, this is the fundamental instantons, one instantons on the R4. And when T goes to 0, this converging to some kind of delta connection, delta function. So this is called the bubble. But if the energy is smaller than 1, this phenomenon does not occur. So we have. And another possibility of the end is called the sliding end. So suppose there is some subsequence looks like this. So around here, curvature. So this is a graph of the curvature, pointwise norm of the graph of curvature. And over here, suppose the curvature is small, sufficiently small, and we have some sliding end like this. And we will get some contradiction. And near here, the connection is, this connection is close to some flat connection over here. And now this domain contains L1 plus 1 components. Then, because this is a flat connection over here, and we have yi, y plus, and so on, by Pigeonhole principle, here we use Ly is equal to the number of conjugacy classes of SU2 representations space. So there exists J and J prime such that the restriction of rho to Yj is gauge equivalent to rho of Yj prime. So then rho gives a flat connection, rho tilde, on the glued manifold. So this is nothing but J minus J prime X. So which I introduce in the So now I would like to consider the energy. It's a normal curvature of curvature on red part, this part. So this is, by the definition, this is equal to the Chern-Simons value of rho. Sorry, this is rho tilde on this closed form manifold. So this is just a. But our assumption is total energy is smaller than this number. This is our assumption. But this is now the minimal value or irreducible part of these numbers. Okay. So because of that, we can conclude that this, this is tilde. Rho tilde is gauge equivalent to the trivial flat connection. So we can imply that the energy of red part is 0. This gives a contradiction. Yeah, so this is a very rough sketch of proof. Okay. So I have 5 minutes. So now I want to prove the main theorem by using the previous compactness result. So for any further critical point satisfying these conditions, so the Chern-Simons of A is smaller than R, and Freer index of A is equal to 1, then we consider the following modular space. So MA theta. So first, before that, we consider the 4 manifolds, which have both cylindrical ends and periodic ends. So this is denoted by W. Now I would like to consider the modular space of ASD equation on W, which have the following asymptotic conditions. On this side, this converging to A, and on right-hand side, periodic end side, this converging to the trivial flat connection. Yeah, and by using the perturbation theory, we can have the structure of one-dimensional manifold on this modular space. And gluing theory tells us there is some compactification of one-dimensional manifold modular space, and such that the boundary of this modular space are given by as follows. So, and I should say this compactified space has a structure of compact one-dimensional manifold. Okay. So the boundaries of the modular space can be written as follows. So in the first case, we have these broken trajectories. So broken trajectory along the irreducible critical points. So this is nothing but the definition of differential. And this is some cochain. On the other hand, we also have this sliding end. So broke trajectory along the trivial flat connection theta. So this is nothing but the definition of the original theta r. And we can easily see that this is just 1 point. So moreover, there is no other ends because of the compactness theorem. For example, we don't have the following end. Like this. We don't have this end. Yeah, because of the compactness theorem. So we can conclude that this, because of these are boundaries of one-dimensional manifold, oriented one-dimensional manifold, the countings of this part is equal to counting of minus this part. This part. So we can conclude that differential of cochain is equal to theta r. So this implies this cohomology class, the cohomology class determined by theta, vanishes. So this is a sketch of proof. And I would like to say, actually there is alternative proof without using any gauge theory for manifold with periodic ends. So this is my recent work, and I can prove this result. In here, we don't have the condition on the representation space. In my first result, I impose this condition, but here I don't need such kind of condition. And so we can improve the result by using instant Fourier theory, only using instant Fourier theory. Okay, so that's all I want to say. So thank you for listening.
Okay, are there any questions?
So which Floer theory do you use for this last theorem?
Sorry, this one?
Yeah.
Sorry, sorry,
Which Floer theory?
sorry, could you say
You
again?
said you are just using Floer theory. What kind of Floer theory?
Freer's theorem?
Yeah.
Uh,
What kind of Floer theory?
Freer, sorry. Freer's theorem.
Floer.
Freer's theorem. I
Instanton homology, is it?
yeah. So okay, so yeah, I will. Yeah. So the idea is as follows. So yeah, I will. Yeah, this is an application of yeah, Nozaki, Sato, Taniguchi, and yeah, also Daimi's invariants. This is denoted by RS, and this is denoted by gamma K. An application of these invariants. So, and yeah, I would like to say what is a proof. So first, we have an embedding from Y to X, like this. Then we have cobordism from Y to itself. And this is homology cobordism. And yeah, roughly speaking, we consider the following four manifolds. And then this gives for for this cobordism, we can define a cobordism map. And let's say, yeah, so I should say, so suppose theta r is not equal to 0, then we have some critical point such that theta of A is not equal to 0. So sorry, I should say, so for fixed A, we consider that this modular space. And considering the, so before that, I think I should say this RSY is equal to a subpolymer value is of, so when S is equal to minus infinity, that this is equal to subpolymer value of R such that this homology class vanishes. So this is a definition of R minus infinity of Y. Yeah, this is important to obtain the proof only using Fourier theory. So yeah, so actually, if this is finite, then we can take a critical point such that this, roughly speaking, this is not equal to 0. Yeah, and like this. Yeah, so when you define the invariant using subpolymer value of R, whose R theta R is equal to 0, then yeah, for if this invariant is finite, then you can find a critical point of Chern-Simons part of the Chern-Simons function whose theta for this R is not equal to 0, and yeah, the Chern-Simons value of A is almost R minus infinity of Y. So this implies A has a ASD solution to ASD equation on Y times R with the smallest energy. So this is some kind of consequence of the definition of R minus infinity of Y. So so now we have the smallest trajectories, smallest energy trajectory. So we have A theta and some smallest energy trajectory. Yeah, for simplicity, I want to say, so this three manifold, the sigma 235 are some, I think, minus. And then the smallest energy instantons has, sorry, this here is not neat, is equal to 1 over 120. So, and if you have embedding from this manifold to homology S1 times S3, X, then you have the homology cobordism from Y to itself. And then you consider this cylindrical and form manifold. And here you consider these are the asymptotic conditions. And by considering the gluing, the modular space has the following ends. The first one is I should say this one. Sorry. This one. And the second one is this one. And there is no, there is other ends coming from the right one. So, I'm sorry, yeah. Yeah, sorry. B is A, B, B theta. That's all. And I think that's all. Yeah, we have these ends. So, and here we have a minimal energy. Sorry. Yeah, and since the total energy is now 1 over 120, so yeah. And actually, sorry. Yeah. Sorry,
No, that's all right. I got the general flavor of the argument.
Sorry. I should say, Now we are assuming Y is homogeneous. Sigma minus sigma 235. We can ignore this part, and in general, there is some method to ignore this part. So and this is non-zero. Now we are assuming. So we can see the count along this ends is not equal to 0. If we can ignore this part, then we have some B satisfying this broken trajectory, and so yes, we can prove this is actually gauge equivalent to A, because now we are considering minimal energy on the total space. So here we again obtained ASD equation converging to the trivial flat connection. So we can we can see that the energy of this part is smaller than or equal to greater than or equal to 1 over 120. So energy of this part is equal to 1 over 120, because we are now considering minimal energy. So, and it also implies B is gauge equivalent to A. So now we have ASD solution to ASD equation whose boundary conditions are A and A. So same boundary conditions. So actually, if you have such condition, we can have a flat connection, because energy of this part is equal to 0. So we have some flat connection. Okay, so this implies there is some flat connection over X. So as a conclusion, we can see there is some irreducible representation of fundamental group of X. This method can improve our main theorem in this talk.
Okay.
This is the main observation.
Okay,
Sorry.
Thank you. Are there any other questions?
I think we should thank Ms. Masaki
Thank you.
Masaki again.
Yeah, okay, thank you.
There are no further questions. I'll log
Just
us off.
before you go, Dave, but let's remind everybody that the next talk in this series is next Thursday at the same time.
Thank you. Yeah.
Anyway, so good. Thank you very much, Masaki.
Thank you. Thank you,
Yeah.
Boris.
Thank you.
See you soon. Bye.